This video tutorial looks at the mathematics of matrices, and more specifically we're going to focus our understanding on different matrix types. Now the first matrix type that we're going to look at is an identity matrix. Now an identity matrix is a square matrix where the values are either 0 or 1. And as you can see, the values running diagonally down from top left to bottom right are going to be 1. Whether it's a 2 by 2 or a 3 by 3, and you'll also see that every other value in our matrix is going to be a 0. Okay, so when we're expanding and simplifying matrices, we can apply similar rules as we do to algebra. All right, so if we're looking at using our FOIL rule, so where we multiply two brackets, all right, using algebra, we've got our first, so we multiply our first elements. We then multiply the outer elements, the inner elements, and the last elements from each bracket. We can do the same thing with matrices. So let's say in our first example, so here is example 1. All right, we've got elements of A and 2I, so 2 multiplied by our identity matrix. Now, if we're going to square that, we can rewrite this as A plus 2I, A plus 2I. All right, so if we're looking at multiplying our firsts, we've got A times A will give us A squared. We're then going to multiply our outers, which is A and 2I, which is 2IA. We're then going to multiply our inners, which is 2I and A, which is 2AI. And then we're going to multiply our lasts. Let's use an orange. We've got 2I and 2I, which is 4I squared. Now, it's important to know that that IA actually equals AI, which also just simply equals A. Okay. So therefore, that's why these two IAs just become 2A's. And we can collect those because 2A plus 2A gives us 4A, and therefore we've simplified by expanding. In our second example, so example 2, we're doing the same process. However, what we end up with is so our firsts give us our A squared, our last give us our B squared, but here we've got minus BA and minus AB. Now they're not necessarily the same, so we should have discovered previously that if you've got matrix A times B, that doesn't equal matrix B times A. So they are not like terms, which means we cannot simplify them. Okay, so you can't simplify when you expand in that particular example. Now the next type of matrix that we're looking at is a state matrix. So basically a state matrix is a matrix that represents the current state of a given system. Now we denote this as S. Okay, so this can change over time, and most of the time, well, we're going to identify an initial state matrix. So that's the initial system, and that's denoted as S0. Now the next, or if there's a change to the current system, so we start with S0. If there's a change, we now have a state matrix of 1. If there's another change, a state matrix of 2. If there's another change, a state matrix of 3, and so on and so on. But essentially, the initial matrix can be used through this example. So if we're looking at example, the brand Ace makes ice cream. It currently has 60% of the market share. So that means 60% of people who eat ice cream are going to eat Ace ice cream, and the rest of the population is going to eat another brand. So therefore, our initial matrix or initial state matrix, okay, has 63 or 0.63, which is 63% as a decimal, under Ace, and 0.37, which is again the rest of the market share, because remember that a market share has to equal 100%, goes to other brands. So 100% take 63% is going to be 37%, which is then going to give us 0.37. So another type of matrix that we're going to look at is a transition matrix. Now, a transition matrix is used to model how a system might change over time. Okay, and this is generally denoted as T. And we can see this down here, where T is equal to our transition matrix. Now, basically, we can use, by analysing the market, we can determine the following information in the example with the ACE and the ice cream. So we've got in buying now, we've got ACE having 80% and the other group having 20%. All right, and we can see so 80% is here and 20% is here. But buying next week, okay, so we're going to have 30% of the others and 80% of them. So we're going to look at this. So this gives our matrix, and most of the time you'll be given this in a table. All right, and feel free to pause the video and have a quick read of what the different sections in that table actually represent, because it's important that you understand that before you move on. Okay, so we can use our state matrices and our transition matrices to determine any changes in a system over time. All right, so as we see here, we've got, after 1 week, the proportion of people who will be buying ACE is 80% of the 63% because they had 0.8. So that is this part here. All right, of the 63% who currently buy ACE, 80% are going to continue buying it the next week. Plus, we're going to add 30% of our 37% people who weren't buying the ACE ice cream. Okay, now basically what that means in simple terms is we're going to multiply our transition matrix, okay, which is here, by our initial state matrix, which is there. And that's going to give us our new state matrix. So this becomes S1. All right. If we were to find out S2, we would simply be able to say S1 times by our transition matrix would be S2. Okay, and so on and so on. Our S3 would be S2 times by T, and then we can find our state matrix after a certain amount of time. Now, eventually, when we keep finding these new state matrix, we're going to end up finding a steady state, okay, which is basically the matrix that doesn't change. So as you can see here in the example, we found after the 8-week change, if we're going to use the ice cream example, all right, it's 0. We had 0.60 and 0.59. We had 0.39 and 0.4. Now you can see that basically they're all pretty close to the state matrix, or the matrix at our state of 16. So after 16 weeks. So once those numbers don't change, or relatively have a relatively small change, then we can say that we've found a steady state. Okay, no matter how many times you increase the changes in that system, there's going to be consistency between those numbers, and that's what we call the steady state. Okay, so there's a couple of ways we can find the steady state. Like I was doing before, I gave a bit of an example of this stuff here, where S1 was S0 times by T, S2 was S1 times by T, S3 was S2 times by T, etc., etc. But you'll notice that we can also just times our S0 value, not our S theta value, our S0 value by T, and we can actually do T to a power of N, all right? So, and that'll equal our state matrix to that amount of times we're doing it. All right, so that's an important formula for you to figure out. Rather than doing the arduous process of going through the different state matrices, you might just be able to put the transition matrix to a power, and that'll give you an example. Please feel free to pause the video and just read this section down the bottom. It'll go through how we can, use algebra, okay, to identify a matrix. Now, just by looking at these, all right, we had, if you're not sure how they get 2a equals 3b, 0.8a plus 0.3b equals a. If I'm going to take 0.8a, I've got to do that to both sides. That actually means 3b equals, 0.3b equals 0.2a. If I multiply both by 10, I end up with 3b equaling 2a. And you can do something very similar. So I looked at this one here. You can do something very similar with this one here, all right, to make sure that you end up with 2a equaling 3b. We then rearrange to get B equals 2/3 A. We then substitute back in to here to find out that A is going to be 5/3 and B is going to be 0.4, which were the numbers we actually ended up with on our previous slide, just using algebra. Please see me if you're interested in going through that in a little bit more detail. Okay, so here's a practice question I'd like you to have a go at. It gives you some various information about a local high school. Some students bringing their lunch from home and some students buying their lunch from the canteen. It does give you enough information, obviously, to work out your table and then to work out your transition matrix from there. I would use the information from the state matrix to be able to work out how many students you would expect on the next day, which would be Tuesday, and then the following day, well, back down to Friday, which would probably give you a state matrix of S4, I would imagine, and then you should be able to find the steady state proportion of students who buy their lunch at the canteen. Okay, so you should have been able to figure out that this would have been our table that we've used. Okay, so we're talking about 30% brought it from home, 70% brought from home, 30% didn't. They had to go to the canteen. And then lunch tomorrow, you should have worked out these different values here based on the information that was in the question. That would have given you a transition matrix of 0.7, 0.3, 0.5, and 0.5. The initial state then, you would have been able to work out how many students there would have been from home and from the canteen. So that would have been the state matrix. All right. Now you could work out then that round to the nearest student by multiplying those number of students by the matrices or the transition matrices, you would have figured out that there was 151 students are expected to buy their lunch at the canteen the following day. All right. And again, like I said, the state matrix of 4 would have given you the answer for Friday. All right, so you've just got to put the initial state matrix and then the transition matrix to the power of 4. And then eventually you would have figured out that the steady proportion of buying lunch at the canteen is probably going to be 3/8 or 37.5%.